All right. So this next part here, guys, we're going to go over, okay, both position versus time and velocity versus time graphs. Now, you've done basically everything we're going to do with these two graphs in Science 10. We're going to review them and talk about them in a bit more detail, hoping to kind of help you have a better understanding of how to read and interpret them than you did in Science 10. Because I always find when I teach Science 10, people just memorize everything, okay, to do with the graphs. And I want to teach you how to interpret each graph individually. Reason for that is, well, you could just memorize what's on a position time graph and velocity versus time graph. That'll only get you so far. We're going to go over a dozen different graphs in Physics 20. That's a lot of stuff to memorize. We're talking about memorizing everything from 12 different graphs. You get to Physics 30, and it's anywhere between 35 and 50 different graphs. And that's becoming kind of insurmountable in memorizing, okay, what does the area under the line on that graph represent? And what does the slope on that graph represent? And I got to memorize that for 50 different graphs. No, not likely. Okay, you're better off to just treat each graph individually and analyze it as you go, okay, as opposed to memorizing something and then getting it wrong. Okay, so that's what we're going to look at. So we got to look at what information can be read from the graphs and how we do that. Okay, interpreting the graphs, and then looking at how graphs and the equations that are on our formula sheet actually come from the same place. Most of those equations are derived from the graphs that we're going to look at. Okay, so that's what we're going to look at today. Okay, so on a position versus time graph, okay, the title tells us what I can read directly off the graph. Position and time. In other words, I'll know where the object is at any point in time that is recorded on the graph. Okay, that's what I can read directly off the graph. I can interpret or infer lots of other things by looking at the graph's shape and patterns. Okay? As long as I understand that what the graph is showing me is where the object is and how it gets there, that can help me to figure out what kind of movements are going on the graph. Okay? So as an example, the graph we have right here, okay, and all the parts are labeled, but for this first part of the graph, the line is straight. It's diagonal, but it's straight. Okay? If the line is straight and tilted upwards, what is the object doing? It's not accelerating. It's moving at a constant speed, or even more specifically, in this case, it's moving at a constant velocity in a forward direction. Or even more specifically, it is changing its position at a constant rate in a forward direction. Okay? Because if this line is going up, is the position changing? Yeah, because the y values are changing and position is on the y-axis. Okay? So it's changing its position at a constant rate. Okay? Every second it changes the position by the same amount. And any change in position over time is velocity. Okay? So it's moving at a constant velocity. Right? That's not a matter of memorization. That's a matter of I looked at the graph and what was on it and let that tell me what was happening as opposed to memorizing what was happening. Okay? In the next part of this graph, I've got a line, but it's curving. And the curve is getting flatter and flatter. Okay? So is the position of the object still changing? Yes. Is it changing at a constant rate? No. Okay? If the slope of the line is changing, and that's what's happening when you have a curve, okay, then you know that the rate at which it's changing whatever's on the y-axis, in this case position, is changing in a non-uniform manner. Okay? That means that this object is slowing down because the amount of the amount of change in position each second gets less and less and less until it becomes 0. Yeah. Okay? If the line is getting flatter and flatter and flatter, it means it's not going as far each second as it did the second before. And the only way to do that is to go slower and slower and slower until you're eventually stopped. Okay? How do I know that object is stopped? Yeah, its position isn't changing. It stays at a position of 0 for 0.2 hours. Okay, while it's stopped at a train station or something. Okay, everybody all right with that idea? Okay, then in the next part of this graph, okay, we see that there's a curve again, but that curve is getting steeper and steeper. Okay, is the position changing there? Is it changing constantly? No. Okay, the amount of change of position is increasing. Okay, so if we just look at it this way, during this 1/10 of an hour, the position changes by that much. During the next 1/10 of an hour, the position changes by this much. Okay, did it go further the next 1/10 of an hour? Well, the only way to go further is to go faster. Okay, that's how we can interpret that this means the object is accelerating. Okay, rather than memorizing that, we can say, oh yeah, logically speaking, this is what's going on. Okay, and the same is true even for the next 1/10 of an hour. Okay, that line just gets longer and longer and longer because the object is going faster and faster and faster. And then during this last section of the graph, we again have a diagonal line, so it's traveling at a uniform velocity of 200 kilometers per hour. Okay. Everybody all right with that? All right. So that's one of the skills you're going to be expected to demonstrate to me. I throw a graph in front of you and ask you what's going on in this section of the graph or that section of the graph. You've got to be able to look at it and tell me. Okay? Interpreting a graph. Doesn't require you to do any math. Just be able to look at the graph and figure out what's going on. Okay? Now, slope calculations. In Math 10, you probably learned that you can calculate slope using rise over run. How many people have heard that before? Okay, so when you use rise over run, you can definitely calculate slope. You're going to go y2 minus y1 over x2 minus x1, and that's going to give you, okay, the slope. That's all well and good, but that's all that formula can calculate. Okay, which is why you were probably also taught this one. Have people ever seen that formula before? Okay, so it's the linear graphing equation. What does M stand for? Slope. Okay, what does B stand for? The y-intercept. Okay, so this on this graph would be B. Okay, and y and x are just the values from any point that is on your line. Okay, so there'd be a y and an x value for that point. Okay, for B, B is what y is when x is 0. Okay, everybody all right with that? Right. So the advantage of y equals mx plus b is not only can it calculate slope, but it can also extrapolate for values of y and x that may not be on the graph. So as an example, if my graph only went up to 10 seconds, and I knew what the slope of the line was and what b was, I'd be able to calculate where the object would be at 100 seconds. Okay, because I would know what m is, I'd know what b is, and I'd know x is 100 seconds. Even though that's not on the graph, the graphing equation would allow me to calculate it and extrapolate for a value that is not on the graph. Okay, that's the benefit of using y equals mx plus b. It can calculate things that are not only on the graph, but also not on the graph. Okay? All right, if I manipulate this for m, what does this formula look like? What should I move first? B. Okay, we did this yesterday, right? So we said y minus b divided by x equals the slope. Now, you probably memorized last year that the slope of the line on this type of graph represents what does the slope of a position versus time graph show you? Oh. Velocity. Okay, the slope of a position versus time graph is velocity. Here's why. Okay, so I just set this up to calculate slope. Okay, on the y-axis, what's on the y-axis? Position, right? In meters. Okay, this y would be my final position. B would be my initial because it's where I am at time 0. What's on the x-axis? time. Okay, so if I substitute that in, y was final position, b was initial position, x was time, what does that calculate? Velocity. That's total displacement over total time. Okay, that's where v equals d over t comes from. Okay, we derive that formula from the slope of a position versus time graph. Okay, so again, this is why you don't necessarily need to memorize what everything represents. You can figure it out. Okay, I manipulated for slope and then I figured out what did everything represent. Y is a position, b is a position, x is a time. Okay, when I take change in position over change in time, I get velocity. Okay, I don't have to memorize it, I can just figure it out. Right? Same is true for any graph. When we get to the velocity versus time graphs, we'll see that the slope represents something else. Calculate it in the same way, but it represents something else. Okay. All right, everybody okay with that? All right, so here's a typical question I would give you on a quiz or a test. Okay? What is the object doing in part A? It's moving forwards at a constant rate or a constant velocity. Okay, how do we know that? Well, every second it goes the same distance. Okay, what's going on in part B? It stopped. Its position is not changing in part B. What's it doing in part C? Moving in a negative direction. Is it doing that in a constant way or a non-uniform way? It's a constant way, right? It's moving backwards at a constant velocity. What's going on in part D? It stopped. Where is it going faster, E or F? E. Okay. How do we know? Well, it actually goes about the same distance in both parts. But in part E, it does that, crossing that distance in a smaller amount of time. Okay. In other words, it's steeper. Okay. And we just finished saying that the slope of a line on this type of graph represents velocity. Steeper it is, faster it's going. Okay? Those are the types of interpretations you'd be asked to do. All right, here's some of the calculations you'd be asked to do. What's the total displacement of that object over the whole trip? You should be done now. Yeah, it's 0. Okay, how do we know that? Well, we know that the displacement of an object is final position minus initial position. What's my final position? 0. What's my initial position? 0. No. Then I didn't go anywhere. I ended up back where I started. Okay? All right. What's the total distance traveled? That'll take you a little longer. Remember, distance is scalar, so it doesn't care what direction you go. See if you can figure out what the total distance traveled is. Okay, how many people think they got it? Okay, how many people need a minute or two? Okay, we're ready to just go over it then? All right. If I want to calculate the total distance traveled, I need to figure out how far I go in each section of the graph. Okay, because it's not a matter of where I end up and where I started, it's a matter of what did I do in between. Okay, so in part A, I go from a position of 0 to a position of 6. How far did I go? 6 meters. Okay, how far did I go in B? 0. All right, from here to here is another 6 meters. Okay, and then from here to here is another 10 meters. And then, do I have to calculate these separately? No, from here to here is how far? Another 10 meters, right? Okay, so 10 meters plus 10 meters plus 12 meters is 32 meters. Okay, remember, it's scalar. It doesn't care whether it's forwards or backwards, just how far did I go over the course of the trip. Okay, 2 more calculations you might be asked to do. What's the average velocity over the whole trip? You should be done now. It's 0. Why is it 0? Because the displacement was 0, right? Velocity is displacement divided by time. If displacement was 0, velocity is 0. Okay, what's the average speed? Sorry, assuming it goes to 18 seconds. Sorry. Okay, assuming the whole trip takes 18 seconds, what's the average speed? Yeah, it's like 1.77 or something like that. Yeah. Okay, so how do we calculate it? Well, we say average speed is total distance, 32 meters, divided by total time, which was 18 seconds. Okay, so that should give us 1.8 meters per second. Those are the types of calculations you'd be expected to do from this type of graph. Okay. Now, when we did the garbage truck question, remember we said it's important to realize that the 2 parts of that trip didn't represent equal parts of the trip. Okay, so we kind of weighted it in favor of the longer part of the trip. Okay, that's what this graph here is kind of showing. Okay, during the first 0.02 hours, it travels at only 50 kilometers per hour. During the last 0.01 hours, it travels twice as fast. Okay, but it only does that for 1/3 of the trip. 2/3 of the trip is spent at the smaller velocity, right? So our average velocity is going to be closer to the smaller one because it represented a bigger part of the trip. Okay, so by going total displacement over total time, we're essentially weighting the average in favor of the longer part of the trip. Okay. All right. If we're looking at this graph here, okay, what's the object doing in the first part, first 2 seconds? Traveling at a uniform velocity, right? In what direction? Forwards. Okay. What's it doing here? Stopped. What's it doing here? It's accelerating which way? Backwards. Yeah. Okay. The line's getting steeper, but it's getting steeper in a negative direction, right? So that would be running backwards faster and faster. Okay. Then there'd be a section here where it's essentially traveling at a constant speed, and then here we see the line getting flatter and flatter. So during this part, the object is slowing down, right? Okay. And then here it's standing still, and then accelerating again on the other side. All right. So important for us to be able to interpret a graph like that, because occasionally you might get a graph that looks something like this. Okay. Now, this graph is all curves. It's still a position versus time graph, but it's all curves. Okay, so what's going on in this first section here? Right, it's accelerating. The line's getting steeper and steeper. Okay, and then what's going on here? Actually, let's just say between here and here, what's going on? It's slowing down. In fact, it's coming to a stop. Okay, and from here to here, what's it doing? It's accelerating backwards. Which way was it accelerating here? Backwards. If it wasn't accelerating backwards, would it have stopped? It wouldn't have. Okay? Look at the 2 sides of this graph. Do they look the same? Like they're a mirror image of each other, right? Okay? Because they're a mirror image of each other, that tells us that they're the same type of motion. What's different is this one was accelerating backwards, but still moving forwards. Here, it's not only accelerating backwards, it's also moving backwards. Okay? And then during this section of the graph, it's slowing down because the graph is getting flatter. All right, what is this a graph of? That's a tough question. It's a graph of this. Okay? It's a graph of somebody throwing something up in the air and then catching it. Okay? This part of the graph right here is the part of the graph where I'm accelerating the marker. I'm throwing it up in the air, making it go faster. As soon as it leaves my hand, what's it doing? Slowing down due to gravity, right? So it's actually moving upwards, but accelerating downwards at 9.81 meters per second squared. That's the acceleration due to gravity. Okay? So it slows down, comes to a stop, and then actually starts to move downwards. At what rate? 9.81 meters per second squared. Okay? Its acceleration is the same on both sides. It's just the direction of movement is different. Okay? And then this part is where I catch it. Okay? I catch it, I slow it down to a stop in my hand. Okay? That's a pretty high level one. Like to figure out exactly what was going on, and that is tough. Okay? All right. Once in a while, you'll be asked something like, what's like the instantaneous velocity of this object, or how fast was it going at this point in time? Now, on a graph that's all curves, that's pretty hard to calculate, because velocity on this kind of graph is slope. And what's the slope always doing here? It's always changing. So I'm supposed to calculate how fast this thing is going at some point on that curve. Okay? That's pretty tough. Because, you know, to calculate slope, I need 2 points on the line. And I don't have that. Okay? I have a curve, not a line. Okay? So what I have to realize here is that this curve is really an infinitely large number of infinitely small straight lines strung together. Okay? That's what a mathematician sees when they see a curve. They see a lot of little tiny straight lines that are put on the end of each other and are gradually increasing in slope. What they see is what you see when you watch a video on YouTube, but you've got a really slow connection. Okay? And it just gets all pixelated, and you can see all the squares. Okay? That's what they see when they look at a line. A line is really just made up of all these little straight edges, because that's how a computer makes curves. A computer can only make boxes. If the boxes are really small, you don't notice them. Okay? So if you're watching something on your 4K TV at home, the pixels are so small that you can't see them, and the picture looks really sharp. Okay? If you're watching that, you know, on your phone and with a bad connection, and it's playing it at like, you know, 120p, okay, it just looks like a bunch of blocks moving around, okay, because it's low resolution. You can see all the straight edges, right? That's what we see here. So if I can get the slope of one of those really, really small straight lines, I would know how fast the object's going at that point, wouldn't I? Okay, now you're not going to be asked to do this, okay, but you kind of need to know how it works, okay? If I want to make one of these little tiny lines longer, what I have to do is draw a special kind of line. What do we call a line that touches a curve but doesn't cross it? Starts with T. Tangent. Yeah. I have to draw a line that's tangent to the curve where they're asking me. Okay? So I would take a ruler if I was you. With me, I'm going to cheat, and I'm going to use the line tool. Okay? And I would draw a line that touches the curve. Whoop. I'll just move the picture rather than the line. Come on, line. There we go. Okay, and I'm going to make that line touch the curve, but not cross it at about that point. Now that I have that line, would I be able to calculate its slope? Yeah, probably. If I made it go through the right places, but yeah, I'd be able to calculate its slope. Okay. Now, what do we notice about the slope of this curve as we go along? If I keep moving that line, what's going to happen to it? It's going to get steeper and steeper. Okay. What is it going to look like when it's right here? It's going to look flat, exactly. Right? That line is tangent to the curve at B. And we just said that at the top of its flight, that object would stop, just for an instant. Okay? But it would stop, and you have a velocity of 0 for an instant before it started falling back down. Okay? All right. Everybody okay with how that works? Good. Okay. I want you guys to try this one. It's actually question number 12 in your workbook. I know it says 5 here, but it's question number 12 in your workbook. If you want to be able to blow the graph up a bit bigger, okay, you can try that. I don't think I can make it any bigger the way I've drawn it here. Okay, I want you guys to try this question. So it's a position versus time graph. Okay, we're looking for the average velocity in each of the three sections. So this would be section A, B, and C. Okay, and then over the whole trip as well. So to calculate the velocity in part A, okay, so for part A, our velocity is going to be the displacement divided by the time. Okay, and our displacement, we go from 0 to 25. Our displacement is 25, and our time is 1 hour. So that one's really easy. Okay, we're simply going to have 25 kilometers per hour, and that'll be positive because it's going forwards. Okay. Now, during part B, I need to do a similar thing, except I don't start at 0 this time. Okay, so I'm still going to do V equals displacement over time, but I'm going to look at it final position minus initial position divided by time. So that's going to be 33, positive 33, minus 25, where part B starts. And that takes 1 1/4 hours, because it goes from 1 to 2 1/4. Okay, so to here. All right. So when I do that, I have 8 divided by 1 1/4, which should give me positive 6.4 kilometers per hour. Okay. Questions on that one? Okay. Similar calculation for part C. Okay, so our average velocity in part C will be final position minus initial position over time. Okay, so we're going to have a final position of 27, an initial position of 33. Okay, and our time, we're going from 2 1/4 to 3 1/2. So that's another 1.25 hours. Okay, so our total displacement's -6 this time, divided by 1.25, which will give us our negative 4.8 kilometers per hour for part C. Okay, everybody follow me on why it's negative there? Okay, I mean, the object's moving backwards in part C. Okay, over the whole trip, okay, same calculation we've been doing all along. Average velocity is total displacement over total time. Okay, my final position is 27 meters. Okay, my initial position is 0, and the total time is 3 1/2 hours. So 27 divided by 3 1/2 should give me positive 7.7 kilometers per hour. Okay. Everybody all right with how that one works? Okay, so that's a pretty typical position versus time graph type of question that you might get, okay, and be asked to do those kinds of calculations. All right.